All right, so we're going to start rotational motion now, and we know a little bit of it in terms of like what rotational motion is, and kind of really what it isn't. But the great thing about rotational motion is that everything that we already know already applies to this rotational motion. Okay, so previously we talked about circular motion, and while rotational motion and circular motion both deal with like circles and things moving around in circles, they're different. So in circular motion, right, we dealt with an object going around in a circle like this, right, traveling in a circle, and there was some sort of centripetal force that was pulling it around, right, pulling towards the center of that circle, causing it to constantly change its direction so that it would travel in a circle like this, right? So the difference is that with rotational motion, we don't have a single object going around at some sort of radius in a circle, almost like in an orbit, okay? In rotational motion, we have an object itself that the entire body is spinning, okay? So if we're talking circular motion, we could say that that is the Earth orbiting around the sun. If we're talking rotational motion, that is the Earth spinning on its axis. Does that make sense? Okay. Another example would be there's always like they talk about the ladybug on the record player, right? Circular motion, we're talking about the ladybug going around in the circle, right, a certain distance away from the center of this record. But if we're talking rotational motion, we're talking about the entire record player turning and spinning like that as they call it rigid body. Okay, does that make sense? Okay. So that's the difference that we need to think about in terms of the difference between circular motion and rotational motion. But the nice thing about rotational motion is that we already know everything that has to do with rotational motion. We just need to change our vocabulary a little bit. Does that make sense? Okay. So we know that in linear motion, right, we're going to make a little chart here, and we're going to try and come up with as many of these things as we can. Okay? In linear motion, what variable do we use for distance, maybe, or position, right? We could use x, right? We could use y, right? And we've never really done it, but we could also use z, right? So position, we use x or y, and if we want to, we could also do z. Now, in rotational motion, we don't have that x, y, and z, but we have similar things, right? Instead of like, left, right, up, down, in or out, we're talking about the angle that this thing may rotate through, right? So we would call it theta. So if we're talking position, we're talking about theta, okay? Now theta is the distance that it travels in that angle as it goes around. Does that make sense? Okay? Instead of, now speed, we use, right, the letter V. Instead of that, we now use the letter omega, which you'll see usually as like a italic W, right, an italicized W. Okay? Another term we would have would be acceleration, right? But instead of acceleration using A, when we're talking about rotational acceleration, or you'll see a lot of what's called angular acceleration, we use the Greek letter alpha. Okay? What's alpha? That is angular acceleration. All right? So what we're doing right here is we're doing this thing called analogous equations and analogous things. Okay? Okay? Okay. So all we're saying that if we're talking about rotational motion, instead of velocity, it's omega, which is angular speed. Okay? Now, how about force? Right? A force that causes acceleration. Right? Instead of we've got the linear, we're talking force, but rotationally, we're talking about torque. So the rotational addition or the rotational counterpart to force is torque. Okay? Mass is another big one, right? M. But when we talk about mass in terms of rotation, it's this thing called moment of inertia, okay? And that gets capital I. M, mass, right? Mass. I is moment of inertia. So that is the rotational analogy to mass, okay? Oh, what else could we have?
Is it like still in kilograms? Or
It is in something different. When we get to it, it's like, oh, what is it? Kilogram meter squared, something like that. Okay. So in moment of inertia depends on the shape of the object. Okay. We'll get into all of that. It's not a big deal. So another one we may have, we've talked about energy, right? Right? Energy, we have K or U, right? It's still K or U. They're just a little bit different in their equations. We'll get to the equations in a minute. Momentum is P. In angular, right? Angular momentum is L. Okay? So linear momentum is P. Angular momentum, we use L. Okay? So again, we have all the same things. We're just now giving them different names if we're talking about rotation. Okay? And I have a chart that I'll give you as well that gives you a lot of this, okay? But what I want you to see is that they have these counterparts between them, okay? So let's talk about equations. Okay? We've got some kinematic equations. Yep. Well, it'll be force, which would be torque, right? And time, which is time. Yeah, we've never really talked about rotational impulse. Okay. So in linear equations, we've got, let's see, we have x equals x sub o plus v sub o xt plus 1/2 at squared, right? Make sense? Rotationally, it'll be theta equals theta sub o plus omega sub o t plus 1/2 alpha t squared. Right? And, I mean, that's all we're doing is we're taking the linear values that we know, the linear variables, and we're changing them into rotational, right? So all the equations are the same. Their variables are just different. So everything that we already know, like I just said, in terms of kinematics and forces and energy and momentum and all that stuff, is exactly the same. The variables just have new names, right? So if you want to know, what is F equals ma, right? F equals ma, Newton's second law. In rotation, it's torque equals I alpha. So this is Newton's second law in rotational form. Okay? If we're talking momentum, right, P equals mv. Angular momentum is just L equals I omega. Okay? So, I mean, and we know a ton more, right? we're not going to go through all of them. I'm going to, again, give you a chart that has a lot of them on there. But the big thing here is that everything that you already know has a rotational counterpart. And nothing changes except for the variables. The form of every equation is still the same. Does that make sense? Okay? We're just looking at them at a slightly different point of view. Instead of as straight lines, we're talking about them, or even curved line, but in some sort of linear fashion. It's now something that is spinning around itself. Okay? Does that make sense? Okay? And what we'll do, a lot of it is we'll end up talking about it from its center of mass, not from the whole thing as it's on its own, okay?